We have a small group, strange time, but it's being recorded, and I have a feeling that we're going to hear a lot more from Ahmed as we go along. Ahmed Aboelezz is a just starting assistant professor in the Department of Mechanical Engineering. He has a PhD from University of Cairo in aeronautical engineering. And if that weren't enough, he went on to New Mexico Tech to get a PhD in mechanical engineering. And we're very fortunate to have him. I say that because we got to spend a little bit of time together talking about his background. He has, I guess he's been involved in a startup. He's had a lot of different positions in Egypt and has become heavily involved in, amongst other things, drones, which is what we spoke about most of the time. And we all know that drones are out there and what they're being used for. And to see drones involved in climate change research is not surprising necessarily. But I think what Ahmed will show us is that there's tremendous potential that can be realized. And we look forward to having Ahmed involved in our institute, which is the primary purpose for this presentation. He will ideally be joining us as an associate in the very near future. Ahmed.
Thank you, Paul, for this introduction, and good afternoon, everyone. First of all, I am happy to be with you today and give you this presentation. As Paul mentioned, my name is Ahmed, and it's Arabic name, so don't try to say it like I'm saying it. Whatever you will say, I will accept it. In today's presentation, I will try to give you idea how aerospace engineering could be helpful with your researches, and I have already added some showcases. I worked before with groups from mining engineering, a group from electrical engineering, medical groups. So aerospace engineering was very helpful when I tried to collaborate with them. I will go ahead and start the presentation, but I would like give you some brief idea about my experiences and my education. As Paul mentioned, I have two PhDs, one in aerospace engineering from Egypt, another PhD in mechanical engineering from New Mexico Tech here in the United States. I have a bachelor in aeronautical engineering, and I have a master of engineering in renewable energy, and I have a master of science in aerospace engineering. For experiences, I have a blend between academia and industry. So for industry, I worked as a project manager, consultant for some companies. For academia, I been teaching, doing research in different institutions between here and Egypt. So I have a good blend of experiences between academia and industry. So I picked two topics, which I felt it will be more aligned with the research has been done here in the institute. The first one is the drones for harsh environment and the applied aerodynamics. I have multiple research areas, but I feel this will be more helpful in today's presentation. So for the drones point, the drones nowadays being used in everything. You can go to the market and buy one online, so it's easy to get a drone. But I am interested in designing a drone for a certain purpose or a certain need and customizing the design of the drones. This customization helped me to developing drones for mining industry, for helping people in doing mapping, collecting data, a lot of stuff. So the first part of my presentation, I will show you some real cases we developed before. And at the end of the presentation, I will propose some ideas how drones can be used with Climate Change Institute researchers generally. The first project was designing and manufacturing a permissible drone for underground coal mines. Usually, there is a huge restriction in any tools that can be used in underground coal mines. And this tool should be permissible or explosive proof. So making a drone explosive proof will make it very heavy. And the design of this project was very challenging. So we started this project, and it took about 2 years, and it was funded by NIOSH, it's government, but related to the miners' health. And this is, if you can see my pointer, I think. Yes, and was the design of the drone after our phase in the conceptual design and optimizing the design, and this is the final product of the drone. We fabricated it from carbon fiber, and we even developed a new propulsion system. So the propulsion system is a system which gives the drone the thrust or the lifting force. And as we mentioned, we need to design an explosive-proof drone. So the motors should be included inside the drone body. And that's why we use a magnetic coupler, which a new method we implemented in our research. So we have the motors inside and our propeller outside the drone body, and there is a magnetic coupler couple the torque between the motors and the propeller. So the propeller start rotating, and this was a video showing the test flight, which was successful. The problem now, after including the motor inside the drone body, there is no cooling source because the propeller is the cooling source for these motors. And the motor suffer from rising in temperature. Some results or some examples here, you can see this black curve is heat of the motor versus the time. And without any cooling system, the temperature keep rising until motor melting, which is 120 Celsius. So we needed to figure out some solution to cool down the motor, and it, of course, will change the design of the drone itself. To get idea about the temperature of the motor, the performance of the motor, and the propulsion system, we developed this test rig, and this test rig enabled us to measure parameters like the thrust, the temperature, the power consumed, the flow speed through the propellers of this propulsion system. And also we designed these radial heat sinks, which enabled cooling down the motor. And we can see the effectiveness through the blue and the red curves compared with the black one. So the blue and red is different heat sinks, but it enabled us to cool down the motor. Of course, we couldn't do this without this test rig to measure the performance and analysis of the propulsion system. A different project for a Sky company. Sky is company in New Mexico, and they are building stratosphere airships. So they collaborated with our team, and we were trying to design propulsion system for their airships. The idea, they need a propulsion system to altitude change of their airship at the stratosphere altitudes. We started the project by proposing some propulsion configuration. So maybe you have a propeller in one of the fins and the two propellers in the front near the nose of the airship. Maybe you have three propellers at the fins at the end of the airship. However, whatever the configuration, we obtain aerodynamic data because we need a tool to simulate the flight of this airship, and our door to this tool is the aerodynamic data. So we obtain the aerodynamic data. Later, I will give more explanation about the aerodynamic data, how we can obtain it. But once we got the aerodynamic data, we could develop a flight simulation. And in flight simulation, we could predict the flight behavior of this airship in the stratosphere altitudes through software simulation without needing to go to the actual experiment. So first we do simulation, see the behavior, then we do our experiments. Furthermore, we did some experiment and a model for this airship. So the actual airship has a length of 60 meters. So we built this model which has a length of 4 meters, and we use this model to validate our simulation. So when we compare the results from this experiment and the results from the simulation, once it's valid, we can now use the simulation to predict the flight of the big airship. Different project was to design a micro air vehicle, and generally for drones, there is multiple configurations. So there is drones, which we call it the multi-rotor, which have multiple propellers, like the quad one has 4 propellers. And once this propellers rotates like the helicopter, it lifts up this drone. There is another configuration which looks similar to the conventional airplanes, which we call it fixed wing drones, like the one I am showing. And the idea in this project, we want to develop a micro air vehicle, which can fit, for example, your backpack. And if you are in a certain region and you need something to make surveying or anything, you can just get it back from your backpack and throw it, do the mission, collect your data, and come back to you. Usually, you will expect it because it's very small, it's easy. But the idea, it's easy in manufacturing, but its aerodynamics is very complicated, even compared with the conventional air brands. So we spent a lot trying to get some aerodynamic data for this fixed wing drone. And here we can see the drone inside a wind tunnel. The idea, we wanted to collect this data to again generate a flight simulation, predict its flight, and also we needed a tool to validate the equation we are using to predict this aerodynamics. As I mentioned, these platforms had non-linear aerodynamics, which is very difficult to predict. So it was very challenging project as well. Furthermore, we looked at if we have a flapping wing drone. So if you would like to get some data near a wildlife or something, it would be better to have a drone looks like a bird, so you don't scare the animals. So we also worked some time with flapping wing drones, and we can see here in this video, for example, flapping wing drone, and we used the flow visualization using smoke, which coming from here, from this smoke generator, with laser eliminated this smoke, and we can see the wing behavior, how it's interacting with the air, and how the aerodynamics of this flapping wing looks like. Furthermore, we also tried to see if we have a swarm, multiple drones flying next to each other, how these two wings will interact to each other, how I can improve the efficiency of the system if I adjusted the distance between each bird. So also investigating flying in swarm, how efficient this is formations. It's not only about the flapping wing, but also we investigated the coloration. So in real cases, you will see birds full of colors, and we had a hypothesis that mentions that the bird has pattern color because this color improves the flight efficiency. That's why there is pattern. That is why there is no single color for all birds. So we assumed each pattern will improve certain bird flight, and to prove this, we collect some wings with different colors, and we observed the temperature difference between the regions. So the more light regions will give lower temperature when exposed to the sun, more than the dark colors. And also we use this to develop some theory to maybe we can paint our drone with a certain colors, which make it more efficient. So it was inspired from birds' colors. Another also project was to design a dandelion drone. So this is a very tiny drone, and you can have a bunch of them, throw them in the wind will spread them over an area, and then you can collect data. It's a good method to collect data from wide area. Just we needed to optimize the design, and again we used this flow visualization to see how our drone design is interacting with the air. The idea, we need a drone to be gliding for long time, so it can be in air for longer time. Now, I will also mention some efforts we made from the applied aerodynamics perspective and how an aerospace engineers group can contribute to different applications. One of the projects was for the wind engineering industry, and we helped in developing some method to improve the efficiency of vertical flow axis wind turbine. So generally, for wind turbines, there is two famous configurations: vertical axis wind turbine, horizontal axis. So horizontal and the vertical depending on the axis of rotation. So if the axis of rotation here and the propeller or the fan rotating in this direction, we call it horizontal axis wind turbine. If the vertical axis in this direction and this is the rotation direction, we call it vertical axis wind turbine. The vertical axis has multiple advantage. The only disadvantage is the efficiency. It has less efficiency than the horizontal axis. That's why horizontal axis is very popular. And the researchers in this area thinking if we could improve the efficiency of vertical axis and take the other advantages, we are still here. We can make it more competitive with the horizontal axis wind turbine. So we developed a method, we call it guide vane wind turbine, and we assumed by adding a vane in the top surface of wind turbine, it will improve the efficiency. The idea now, I need to know the location of this vein relative to the blade, the geometry relative to the blade geometry itself. So we made our investigation using experimental and computational aerodynamics. So for the computational aerodynamics, we are using computational fluid dynamics simulation, which I may give further details. But generally, we have our simulation and it gives us results, but we don't know if the results is correct or not. So we need a tool to validate the simulation. Again, it's an experiment. So we used this setup, which we developed by our own, and we got measurement about the performance of the wind turbine. Once we have the data, experimental data, we validate the simulation. Once we have a valid simulation, we expand our investigation. Another investigation also related to the wind turbines by using a different method. We call it cross-flow wind turbine, and we install a cross-flow fan at the trailing edge. So the blade of the wind turbine, if you don't know, has an airfoil shape, and the leading edge is a point where it's have the air hit the blade in the beginning, and we have the trailing edge at the end of the blade. So we proposed installing a cross-flow fan at the end of the trailing edge, and we assumed it will improve the efficiency. And to prove the idea again, we built experimental test rig, take the measurement and evaluate the performance. I am just trying to show you some showcases how for something new, we can develop a certain experiment setup and use it. So the same in your investigation. If you need something related to the aerodynamics, we can develop a certain experimental setup to take this measurement and validate your work. It's only not about making a wind turbine more efficient. Also, we need to simulate it, and it's a very trendy topic now to use machine learning. So we have a huge amount of data, and we use this data to train a machine learning model, and then use this model to simulate the wind turbine in some scenarios. For example, this one, to simulate how this system will behave if you are charging electrical vehicle. So we could also use machine learning with our data set to have a more robust and more reliable simulations. Furthermore, I used this knowledge with underground coal mines, and miners usually suffer from a lot of lung disease because during their work period, they inhale a lot of coal dust. So this coal dust deposit in their lung, and they can develop black lung disease or cancers, whatever. So this investigation also was funded by a government. We tried to make some flow simulation to predict what location does this coal dust deposit in the lung. To do this simulation, again, we need to validate our simulation, because whatever the simulation tool you have, it will give you a results, but you need to make sure your results is accurate. That's why we need always to have experimental validation. To validate our work and have experimental setup, it's not logical. Every time we need to do something, we will go to underground coal mine, take measure, and to go back to the lab. The idea now, we wanted to have our underground coal mine in our lab. So we developed dust wind tunnel, which is not conventional wind tunnel like the one used in our aerospace engineering field, but it's developed to make some investigation and help the mining engineers to do their investigation there. The idea with this wind tunnel, it will have a blower to push the air through the wind tunnel, and it simulates the air in underground coal mines. To have dust in this air and make it full with pollution, similar to what will happen in underground coal mine, we in a certain locations, we start injecting dust. And the idea again, which location, what's the dust rate, and the objective to have dust concentration similar to underground coal mines. Some researchers proposed using water drops in the underground coal mine to reduce the concentration of the dust, and they use some water sprays. So the air in underground coal mine is full of dust, water drops, and that's what miners inhale. So we tried to simulate everything happening in the underground coal mine, designing this wind tunnel, And at the end, we built the wind tunnel, validated its performance, and it became very helpful tool for the mining engineering department in my previous institute, and all mining department used it to validate their work using this experimental setup. I have now my mine in my lab, which is our dust wind tunnel, and it's ready for investigating some parameters like my research to measure the dust deposition in the lung airways. So you can, for example, like this image, fabricate 3D printed lung, and you can have cases like lung for young person and young for older person, and you can investigate how aging can affect this particle deposition. Any parameter. Now you have your tools, and it's ready for investigation. So we fabricated our models by 3D printing again, make it in a form which enable us to prepare our experimental setup. And we use this mannequin, which is mimicking a human because this has a human feature like the face, the nose, everything. And we installed them in the dust wind tunnel. And we now ready to take measurement how much dust will deposit in different conditions. So maybe you can change the wind speed, simulating changing the ventilation speed in underground coal mine. You can even change the particle type. So maybe it's silica, not coal dust. Whatever particle types, you can inject it here. So now you have a standard tool to make your experimental investigations. And we expanded our research and made it more difficult. So we needed to see how the air is flowing inside the airways. So we fabricated this. I'm sorry, I will go back. Very sorry. So we fabricated this silicon lung airways, which is transparent, and we used it in experimental setup with PIV, which is particle imaginary velocimeter. The PIV setup has a laser illuminating particles inside the airways, and once it's illuminated, we capture the movement by high-speed camera. With some post-processing and some correlation, we convert the movement of these seeds, which is the illuminated particles, into a velocity field and the velocity vectors. Even we could mimic the annihilation. I just don't know why the video is not working, but maybe. So if you look here, you can see the lung itself is expanding, and this was very difficult experiment, but the result was were very rewarding. So we mimicked the inhalation, and we observed how ignoring inhalation in your calculation could affect the results. Because from aerodynamic perspective, it's very easy to assume it's ignoring the inhalation mechanism. But how accurate is the result? This was a question we were trying to answer. And it wasn't only about doing experiments and get results. We also had CFD simulation, which is computational fluid dynamics simulation. So usually there is some governing equation predict how the flow will fly or go through the airways. And this equation is very difficult to be solved analytically. So we use the numerical and the computational methods to solve these equations. And you can start the process by having your geometry. Again, we have, for example, this long model from a lady in her 16s, and we wanted to investigate how her lung model is healthy. We made our setup modification, parameters, everything, and we could predict the flow behavior inside the airways. Furthermore, we could inject some particles. These particles, again, could be your coal dust. It could be medicine. If you need a medicine target certain region, this could be very helpful for you. And finally, we can see now which regions have more deposition of these particles. The deposition can change with the particle size or injection speed. So the simulation is very helpful, but again, whatever simulation tools, you will have a result, but you need to know if it's correct or not. Furthermore, we used also the dust wind tunnel to see the effectiveness of using dust sensor. So for mining industry engineers, they used a lot of dust sensor and they located in different location. So we tried to help them to give some recommendation where to use this dust sensor, what when the speed limits for using this dust sensor, and you can see this is example of showing how they are interacting with the dust sensor. Sometimes they would like to install multiple dust sensors. So by this investigation, we recommended what is the minimum distance should be between each sensor. Even the orientation, sometimes in a certain orientation, you get a better measurement. So this sensor can be used to measure pollution or the dust concentration. But again, by using some aerospace engineering background, we could give some recommendation to improve your measurement process. So all the previous was showcase what we did before using aerospace engineering in different applications. As Paul mentioned, I am a new assistant professor, so I am trying to building my lab and continue doing the same researches. So I started with Aerosystem Dynamic Performance Lab, which I am building here from scratch. Right now in the lab, I have this drone cage, and the idea, the drone cage is a safe zone to test your drones. Maybe you're designing something, building it, and it's not stable, it's not safe, and it's not good idea to test it between people. So we have this drone cage, so we can test whatever drone, and we can observe it. Even more, it's not about making it safe zone. We have a tracking system, which have 6 high-speed cameras, and we are using this tracking system to predict the flight trajectory of this drone. So maybe we are developing an autonomous drone, and we need to make sure it's the flight path is what we predicted or not. Sometimes also we develop flight controllers, and it's not good idea to test the drone directly without testing the effectiveness of the flight controller and if it's able to stabilize the drone or not. So we don't have it now, but we will have this test rig which enable us to prevent the drone from moving, but allow the rotational movement of the drone. So we can see if our flight controller is stable enough and make a real testing. Once we feel confident, we can test it in the drone cage. More confident, we can test it outdoor. Finally, as I mentioned, we already have some type of research for developing propulsion system. Maybe we need to develop a new propeller for our drones, less noisy or more fit for cold region, more fit for hot regions. So we need a test rig again to measure the performance of our propulsion system. So this is also another thing we will have in our lab. And as I mentioned, I am building the lab now. We have some stuff. We will get some stuff, but it's a matter of time. The other lab is the Applied Aerodynamics lab. And when I came here, the mechanical engineering department had an old wind tunnel. So I am working now in this wind tunnel to fix its issues, provide it with instrumentation, make it helpful, so we can use it in our researches. It's also will include some computer for simulations. So it's not about doing experiment. We can do also CFD simulation like the one I showed you before. How this stuff can be helpful for you. So I think this is the most important topic. And there is a lot of applications. For example, for the drones one, if you would like to use a drone to collect data from certain regions, this region is very cold or it's hard to achieve. So you can use the drones. And as I mentioned, I am interested in customizing the drone based on the need. So if the drone will be flying in cold region, it will have a different design from a drone flying in a desert. For example, how much is your payload? It's very heavy or it's light. How long you would like to collect the data? All of this parameter will affect the customization of the drone. And this is something we did before and we can keep doing it. The idea also is using drones, it's a very robust tool to give the same data. So if you are scanning a region, you can scan the same region for a year and you are sure you are scanning the same region. There is no shifting. Even you can make the process autonomous. So the drone itself can fly, collect your data. This data can be image data or LiDAR or radar data. You can collect, the drone collects the data, go back to its base, it charge itself, fly again. And you can leave it like this for a year, for example, and collect the data. And I don't think there is a conventional way to do this better than a drone. Furthermore, you can also observe the human effect in a certain region, like in urban distance or like deforestation, for example. And usually you would like a tool which is not noisy, and the drone is not noisy. So you can observe an urban location without making the people affected by the noise, and design a drone which is less noisy. And again, you can collect a huge amount of data for very long time. But it's not in one shot. The idea in repeating the same experiment for longer time. Furthermore, if you developed a certain type of sensors, for example, and you would like to locate these sensors in the top of mountain, which is difficult to access, the drone can help you. So we can develop a certain drone, lift your sensor and drop it in a certain location you would like. And you can drop multiple sensors. Furthermore, you finish your mission and you got collected all your data. This drone can go back to the sensor and collect it you again and bring it back. And also, if you have expedition and you would like to deliver some rescue equipment or there is something critical and you have a base far from them, you can use the drones to deliver some rescue tools for these expeditions. Moreover, you can use the drone itself to collect some samples. So you can get samples from water, from soil, from ice, whatever. You can get multiple samples. So you can make the drone cover samples from 1 kilometer square, for example. And you will have a precision sampling and you will know the actual location where you got your samples. And it can be very fast in very cheap way. And again, maybe there is a location you cannot achieve. It's very difficult to reach, so you will use a drone. Similar to the airship project I showed you, you can have an airship flying in a certain altitude, and you can collect air quality data for months, for example. Or maybe you can have like a small submarine under the water surface, and you can keep collecting water quality, for example, for another sampling times. So again, the drones can be used to get you a samples, or itself can help you in getting the samples. Now I am done with the drone application, how it can be helpful. Also, the applied aerodynamics can be very helpful in your researches. So if you are saying the effect of the climate change, and in some regions there is a huge winds, how these winds or storms can affect the urban design of different structure, and you can contribute to this by the applied aerodynamics, even if it's CFD simulation or it's experiment. Applied aerodynamics can be a very helpful tool in this matter. Furthermore, if you would like to do some weather prediction, you will need some accurate wind models, and this also can be developed by the applied aerodynamics. So you can have some CFD simulation or experiment, and they can help you in validate and generate some wind models, which you can use in your climate prediction models. Also, if you would like to observe how the pollution is spread in a certain region, CFD can help you, and it just will need some computational tools, but it's very helpful in this matter. So in this presentation, I just started by showing you real cases, what we did before with people from mining, electrical engineering, medical sector, and how the aerospace engineering was very helpful for them. I also proposed some ideas how you can use drones in your research, how you can use applied aerodynamics, and the main purpose of this presentation to show you our capability and how we could collaborate with you in your researches. Thank you for time and attending, and I hope if anyone have questions, comments, he's welcome.
That was fantastic, an amazing overview. And what we're going to do is, since this is pre-recorded, we're going to send it out to everybody in the Institute and remind them to take a look at this, because there are so many options. Peter, you must have a question. You've appeared on screen.
Yeah, well, thank you. I enjoyed that very much. When I do geodynamics, and we've recently been doing a lot of work with smooth particle hydrodynamics, both in water, in lower viscous fluids, but also in air. And I wondered, can you talk about what CFD you're using particularly there, and if you've got it running on the local machines or if you're using other hardware?
So previously I used ANSYS Fluent, and I am also trying to start using OpenFOAM. You know the problem, ANSYS need to buy a license. This stuff, OpenFOAM is open source.
Yeah.
Sometimes some people try to have, for example, their own turbulence model. And it's not easy to do this with ANSYS Fluent, which is closed package. So using OpenFOAM is very helpful. But again, we didn't use it yet. But let's assume our main packages to doing safety simulation, ANSYS Fluent, and the school have a license, I think. The other one is OpenFOAM.
Yeah, okay, good. And I'm familiar with OpenFOAM, and I also know some of the problems of working on it. But I recommend following that anyway. But if you sometime let's meet and we'll talk about smooth particle hydrodynamics and then integrating it with OpenFOAM.
Sure.
Thank you.
Anytime. Thank you.
Yeah.
Dan.
Hi, Ahmed. Thanks for your presentation.
So there is okay. There was a question from the room. Can we take it first?
Sure, go ahead.
So can you raise your voice because I think they didn't hear you. So it's a problem, and we could study it. It's a very challenging problem. But for example, already researcher from NASA could develop a drone which can fly in Mars, you know, and also it's a very harsh environment. So I am very interested in drones for harsh environment. We could develop something, but if you have some fun, we can go ahead. You know?
I
So
couldn't,
for
I
the
couldn't hear
airship-
that question at all.
So the first question, the lady was asking about if we could develop a certain drone which can fly through hurricane, and I said it's a very challenging problem. It's a cell engineering problem. We can work on it, but we need some funds, and we can try to solve it.
I see. Thank you.
Thank you. So there was also another question about the elevation, right? What is the maximum elevation? For example, the stratosphere airship, it's flying in the stratosphere altitude. So again, you can control the elevation by customizing the design.
Okay.
Yes, so the other question was if I showed a slide about collecting samples from water, and if it's possible to collect samples from ice from high elevation. Yes, it's possible. Again, it's an engineering problem. We will just try to work on it, and that's why also I showed you the permissible drone. It was very difficult project, you know, but with hard working and with good funds, we could make it. So there's probability it can fail, but there is probability it can work. So we are good here. So you can go ahead. I'm sorry.
No problem. Yeah, I'm wondering, you know, drones are inherently limited by their batteries and the capacity of their batteries. Now, if they're going to operate in very cold conditions, you know, high elevation or polar, plus very windy conditions, the batteries are going to be drained to fight the wind and also to combat the cold. So I'm wondering, at what point does the size of a battery become, you know, unfeasible for a drone, and when would it make more sense to use a drone compared to using a plane, an aeroplane, fixed wing or something?
Thank you. It's a little bit difficult question, but the idea, for example, if you will get a drone from the market, which is the Chinese one, for example, it will fly for 20 minutes. And if you used it in cold weather, this time will reduce a lot. And that's why I am spending some good time in designing the drone by myself. So if I am proposing something you can just buy, it's not a good idea. But again, back to the permissible drone we made. We already changing the drone design. Even I forgot to mention that, but even the battery used in this drone, it was a different design. We had a group worked with us from electrical engineering, and they tried to make sure this batteries doesn't explode. So it was a different battery. Based on your question, there is limits. You are right, totally right. There is a limit on the drone use. But the idea with the drones, you can use multiple of drones and they can fly like a swarm and they cover more area. Or you can make the drone repeat the task. So for example, it can collect samples for 20 minutes and it can go back to the charging station, charge, and go to another mission. So the idea is not to do the task in one shot. It's just doing it in a different way or in a smart way. And again, maybe you have a higher payload weight. So you don't have to use a multi-rotor drone like this. Maybe you can use the fixed wing drone. That's, as I mentioned, there is some types. So these fixed wing drones have a very long endurance in flying. But the problem, it cannot take off and land in vertical. It needs a small runway. So it's easier to use this one. But the problem, this one has a less flying time, less payload capability. So again, it's just customizing the problem based on your need. And you know, there is some hybrid drone which have both of them in one configuration, and we call it vertical take-off landing drones. So whatever you need is, that's my interest. I am trying to modify the design based on your needs.
Okay, thank you.
Unless is there somebody in the audience?
Yes,
Okay.
yes, there's another question. So this one question was about what type of drones I am interested in and which one I would be interested in developing. So generally, I worked in both types. So I worked with fixed wing drones from designing and manufacturing it and the multi-rotor. But I am also focusing is not only building the drone. I'm just searching for needs. And that's the main objective of the presentation. I'm trying to understand your needs, what conditions this drone will fly in, and I start customizing the design based on your needs. So fixed wing, multi-rotor, hybrid one, all of this stuff I've been working with before. What I should use it for? For me, I am aerospace engineer. I am like to build it. But for me, I'm looking you as you are my customer. You are the one who needs the drone, and I am changing the design based on your needs. But for me, I'm just building and the flight.
If I may ask a question, unless there's somebody out there, we had a fantastic discussion about the possibility of using drones for picking up water samples, a variety of other things. And I was wondering, since the power is obviously a big issue, have engineers considered having solar panels of some sort or some solar collector on the props? I have a boat and it has a sump pump on it. It requires a tiny solar panel to keep that 12-volt battery powered. And no matter how much water seems to get pumped, it always manages to keep up. Has that been considered?
Yes, so there is some UAVs, some fixed wing drones like this one have solar panels in the wing because you have a big wing area which could fit solar panels. The only problem, the airplanes should be very light because you cannot have a heavy power consumption. And to make it light, the structure becomes very flexible and it gives you some limits on the wind disturbance. So if you are flying in a windy weather, it will not be good. It would be easily to be broken. So it's very good. You can have a very long endurance by hours. But the only drawback is the flexibility and the weakness of the structure, because you need it very light, you know. That's the only problem.
What about having one of the helicopter type drones that when it begins to run out of power, sits down for a while and has panels that can draw power and then lift off again? Is that being considered?
So the problem with the multi-rotor or the helicopter one, it's consume more energy than the fixed wing. That's why the fixed wing can fly for longer time and they have more payloads. So it's not very applicable. But for example, the one they used in the March, it have smaller solar panels. But the idea there, the gravity is much less than what we have here in the Earth. So it was applicable here, but in the Earth, it's a little bit difficult to use solar source for the multi-rotor drones, but it can for the fixed wing.
Right, except that the multi-rotor is the one that's more effective in actually going down, picking something up and coming back up again.
So for the multi-rotors, there is different configuration. So you can have 4 rotors, you can have a single rotor, which is the helicopter. The multi-rotor has the advantage of hovering in the air and the takeoff and landing in a vertical position. It's only disadvantage in the endurance. It have less endurance.
Right, which is why I was thinking that solar related to that would be good, even though it doesn't have the large surface area of the fixed wing.
Yes.
Are there any other questions out in the audience?
We're good. You are good here.
Okay, well, thank you. That was
Thank you.
fantastic. You gave us a great review of drones and many of the things that we can use and work with you on for climate change.
Thank you. I appreciate it and appreciate the time I've been give to give this presentation. Thank you.
Thank you.
Thank you. Thank you.